Welcome everyone to this exciting webinar. We'll just give it a moment for everyone to log in. I know Zoom is sometimes a little slow. Everyone, thank you very much for joining this webinar, which I'm certainly very excited for. On atomic scale insights into energy materials, including batteries, by Prof. Saiful Islam from the University of Oxford. And this webinar series is a collaboration between IUPAC, CHEMRAWN, and the IYCN and Beyond Benign. So very quickly, before we get into what we are all here for, an introduction to who each of those people are. So the IUPAC is the International Union of Pure and Applied Chemistry, and essentially they are the people who come up with the names for things, the periodic table, names of elements, terminology, and all sorts. But they also do so much more. So CHEMRAWN is one of the standing committees of IUPAC and focuses on chemical research applied to world needs, such as the fantastic energy materials we'll be talking about today, but also there are several other activities, such as the Global Conversation on Sustainability, which runs every year towards the end of September. We have Chemistry Entrepreneurship, which is another fantastic webinar series, which is led by COCHI, so that's the Committee on Chemical Industry, and this series, which is Promoting Chemistry Applied to World Needs. The IYCN is another committee which is part of IUPAC, and it's run by young chemists and early career chemists around the world to help support early career chemists, run events, and develop professional networks. Together, the IYCN and IUPAC run GCS Day, which is the Global Conversation on Sustainability, which, as I mentioned, runs towards the end of September every year. And there is a special symposium as part of the IUPAC 2025 General Assembly and World Chemistry Congress. And I believe the abstract deadline for that is April the 15th, not April the 5th. And they like to give it it's the late breaking abstracts. So you even get a special name for your submission. I will hand over to my colleague Juliana to introduce Beyond Benign, who was one of the other collaborators on this project.
Thank you so much, Ollie. Thank you all so much for being here. I just want to say that Beyond Benign is thrilled to join all of you in this collaboration. We are a nonprofit dedicated to implementing green chemistry into education. We have a lot of different initiatives and projects. So if you want to keep touch in what we're doing, please check out the QR code that's going to take you to our newsletter. And we can send you reminders and content about green chemistry education, so you can keep in touch with us. So thank you so much, Ollie.
Fantastic. Thank you very much, Juliana. Then onto this project, we are, of course, looking at promoting chemistry applied to world needs. And here we have some of the UN Sustainable Development Goals. And we are, as part of this project, in addition to the webinars, we'll be producing several short resource videos, which will be accessible for schools and those interested in chemistry and how it can be applied to making society sustainable. Of course, we've got the top 10 emerging technologies, which are some of the most important ways that chemistry is applied to world needs. Here we have last year's top 10, all of which sound very cool, the sorts of things I imagine you'd find in science fiction novels, aptamers and metallocenes. And there is currently the call for nominations open for the 2025 emerging technologies. So if there's anything you think is missing from the 2024 or previous lists, then this is your chance to get them recognized. And there is also the opportunity to contribute to the Pure and Applied Chemistry special series. Without further ado, onto what we are all here for, which is our talk on atomic scale insights into energy materials from Prof. Saiful Islam, who is a professor of material science at the University of Oxford, working on the atomistic simulation of a whole host of materials, which are very important to the world. So, without further ado, over to you, Saiful, if you want to share your screen.
Right. Is that okay?
That is fantastic, Saiful.
Great. So let me just... Right. Well, I'm going to start with a thank you and then a confession. The thank you is to Ollie, Fran, Chloe, and Juliana for the very kind invitation to give this webinar. The confession is I'm a bit anxious about this talk because it's very hard to gauge the audience. So I wasn't sure about the level to pitch it, about the content, and obviously I don't know much about the audience. So I asked Ollie, what should I talk about? And he said about 40 minutes. So for the next 39 minutes, I'm going to give you a flavour of atomic scale insights into energy materials, batteries included. And since I said it's a flavour, let me start off with the menu. So the menu will start off with a short starter on materials and modelling. Then the main course will be lithium-ion battery materials, particularly the positive electrode called the cathode. And then for dessert, I'm going to talk about perovskite solar cells. And then I suppose an in-between aperitif, I'm going to talk about alternative battery. Basically, when life gives you lemons, what do you do with them? So let me start off with introduction. I think we know that the energy challenge of low carbon energy is a very, very hot topic, both literally and metaphorically. It's a hot topic because of climate change and the climate crisis, and we need to reduce CO2 emissions. So energy storage and energy conversion are probably more important now than any time in human history. So I work in both of those areas. On the left, storage, on the right, conversion. And what's common amongst both of those technologies is materials are key. The discovery of new materials, characterizing them, and then a deeper understanding of how they work. And that is very much linked to the technology, the devices themselves, the manufacturing, their cell performance, and their lifetime. As a material scientist, I very much in the top camp, and that's my research philosophy, but we're always mindful of the technology, which is the bottom panel. So what are the atomic scale issues that I'm looking at in terms of deeper understanding? Well, the first one is, what does the material look like? What is the bulk crystal structure? What is the structure at the local level? Often within these materials, ions move or electrons move. What is the conduction mechanism? Often they're difficult to elucidate from experiment. These materials are intrinsically defective. What is their defects and their redox chemistry? And often they're deliberately doped. So what is the dopant and disorder properties? And if you're looking at nanoscale properties or catalysis or interfaces, we need to understand the surfaces, interface, and nanostructures within these materials. So there's some of the atomic scale issues that we need to understand. And the way that my group tried to understand these complex issues is through materials modeling. And modeling is very much in synergy with experiment. And that's why I'm showing you this kind of yin and yang. A lot of our work, my work on modeling, links up directly with experimental. So on the modeling techniques, it's mainly density functional theory or electronic structure methods. molecular dynamics methods to look at kinetics, and increasingly coupling DFT with large-scale MD through machine learning. Experimental techniques will be synthesis, X-ray neutron diffraction, electrochemistry, and microscopy, but also photochemical and optical measurements as well. So just one more slide on modeling, just to give you an idea of the techniques that we use. Up on the y-axis, I'm showing you time scale, and along the x-axis is length scale. So some very small angstrom to meters and very short femto to years. And on the bottom left is very much the physics and chemistry of modeling atoms and electrons. And that's where I sit, looking at ab initio, DFT, molecular dynamics, and Monte Carlo. And then when you want to look at grains and particles, you might move to Monte Carlo and mesoscale modeling. And then engineering will be finite element and continuum. So as I mentioned before, we can link the high-level ab initio methods, quantum mechanical methods, with large-scale MD by using machine learning methods, particularly machine learning interatomic potentials. So let me go to the main course, the lithium-ion batteries, and introduce their context first. I think we know that there's been what I call disruptive innovation in this field. So back in the 80s and 90s, when I was a university student, when I went to concerts to see the Smiths or the Cure or New Order, that's what the audience looked like. Nowadays, if you went to see Taylor Swift, Coldplay, or Billie Eilish, the audience would look like that, using their mobile devices. And that's because of the disruptive innovation of portable electronics, and that they've been powered by lithium-ion batteries because they show energy storage. In fact, a lot of you are watching this on a device powered by a lithium-ion battery, whether it's a laptop or a tablet. So what's the next challenge? Well, it's happening already, the electrification of transport. So the decarbonation of transport through electric vehicles. So what's inside a battery? So let me explain. So a lithium-ion battery is an electrochemical sandwich. And like any sandwich, you've got two bread slices, in this case, two electrodes. The positive electrode, cathode, is a layered oxide. The negative electrode, or anode here, is made up of layered graphite. And in between the two bread slices, between the two electrodes, is a good sandwich filling. The meat or cheese if you're vegetarian, and that is a very good lithium-ion conductor. In this case, a lithium salt with an organic solvent, and that allows lithium ions to move very quickly between the two electrodes. So when you're charging your phone tonight, you're seeing chemistry in action. Lithiums are moving from one electrode to the other. And then when you're using your device the next morning, you're discharging it. And lithium ions are going the other way, releasing electrons, and that's powering your device. So it's basically electrochemical energy storage. It's extremely powerful and obviously has helped to revolutionize portable electronics. So I mentioned new let me give you a couple of interesting statistics. Road transport accounts for about 25% of all CO2 emissions. And in some countries, that's growing rapidly, like China, India, Brazil. In the UK, in Europe in general, 90% of UK car journeys are less than 40 miles. In fact, 50% are less than 5 miles, to the school, to the supermarket. So if you have a second car, then it's worth having electric, because actually the journeys are very short. So why do we need new materials? particularly on the cathode side. So the conventional cathodes right now in your phone or electric vehicle are based on lithium cobalt oxide, which is a layered oxide. I've shown you the structure where green is lithium at the top and the transition metal layer is in blue. That has a redox of cobalt 3+, 4+, and that'll become significant in a few slides. The other material, which is becoming increasingly important, is lithium iron phosphate, which relies on an iron 2+, iron 3+ redox. The structure is quite different from a layered oxide, and you can see it's made up of yellow iron octahedra and the blue phosphate groups. And I'm showing you the lithium ions in grey. The pioneer behind both those materials, and he won a Nobel Prize in 2019, is John B. Goodenough. And he did a lot of that pioneering work here in Oxford, where I work. For those people who aren't so sure, John Goodenough is the person on the left. The person on the right is a US president who believed in scientific method and the truth. So the cathode is the barrier to high energy density. So basically, we need new materials and some underpinning science to advance this area. And one of the consortia doing this is funded by something called the Faraday Institution, based in the UK. And I lead a project on next generation lithium ion cathode materials called CatMat. And if you need more information, there's a website, catmatproject.com. So first of all, charging. Obviously, we would like the batteries to be charged faster. So what is controlling charging? It's basically the lithium ions moving within the materials. And I'm going to show you something that's in your phone right now. So this is a layered oxide, a layered positive electrode, lithium cobalt oxide. The blues are cobalt, the reds are oxygen, and the lithium ions are in green. And this shows you a molecular dynamics simulation showing the lithium ions moving through the 2D layers. And you can see it's through the sheets of these structures, and that fast diffusion through those sheets is very important. So as in life, the important stuff is happening between the sheets. We can, from modeling, derive what is called a rate of diffusion coefficient, which is 10 to the minus 9 centimeters per second, centimeters squared per second for this material. And the activation barrier is about 0.4 electron volts, 40 kilojoules per mole. We can do this for other materials, and this is the lithium iron phosphate. What I'm showing you here is a slice through the crystal. The yellows are the iron octahedra, the blues are the phosphate, and the greys are the lithium ions. So in terms of atomic scale insights, we can actually look at how lithium ions move in this lithium iron phosphate. And we predicted that it was a 1D conductor, but that 1D conductor wasn't a linear path, but a curved pathway with an activation energy of about 0.5 eV, and again, a diffusion coefficient of 10 to the minus 9. What was interesting, this was a clear prediction from modeling. Years later, through a collaboration between Yamada and Yoshima in Tokyo, they used high-resolution diffraction and maximum entropy methods, and they derived a pathway for lithium shown by the contour map in blue. So their contour map also confirmed that it was a 1D conductor. And that was a nice confirmation of our prediction. But it was nice that there was some quantitative agreement as well between the contour plot and our curved pathway. So that was a nice confirmation of our prediction of that atomistic mechanism. So let me move on to more recent work, and this is to do with lithium-rich cathodes, which I'll explain. So I said to you that the cathode is one of the limiting parts of a high energy density lithium battery. You would love to charge your phone maybe for a week. We would love for the electric vehicle to have a longer range. So what I'm showing you here is the energy storage capacity along the y-axis. Don't worry about the units, it's just basically a relative plot. Along the x-axis, I'm showing you some different materials. The light green on the left is lithium cobalt oxide. The darker green is NMC, which is a layered nickel manganese cobalt material. And on the right, in purple, is the negative electrode, the graphite. And even if you're not a battery chemist, you can see there's a big difference between the energy storage of the cathode and the graphite. So we need to increase the energy density of the cathode. And we're looking at these lithium-rich layered materials and lithium-rich disordered rock salt materials, which, as you can see, have much higher energy density and getting towards graphite. They also have the advantage of being more sustainable because they're mainly made up of manganese or iron. There are issues to do with cobalt and nickel in terms of abundance, cost, and their mining. So let me introduce you to disordered rock salt. I think all of you as chemists would know what a rock salt structure is. It's the stuff you sprinkle on your chips, on your pasta, in my case, before a tequila shot. So the rock salt structure is shown on the left, but with a difference. This is a disordered rock salt, where the cation site is both lithium and manganese. The anion site is both oxygen and fluoride. And the stoichiometry is at the top, Li2MnO2F. This shows a higher energy capacity at first cycle than the lithium cobalt oxide. As I mentioned before, there's no cobalt or nickel, which is a plus. Manganese has high abundance and lower cost. But these materials don't work as well as lithium cobalt oxide or NMC. They've got a voltage drop called a hysteresis, and the nature of the oxidized oxygen is not well established. So let me start off with some simulation work. What I'm showing you here is a plot of the percentage contribution to the redox activity when you charge a cathode, i.e. when you pull out lithium from this cathode material, what happens to the redox process? What is the redox mechanism? At the beginning of charging, on the left, it's dominated by blue, which is manganese redox, manganese 3+ going to manganese 4+. And that agrees with experiments such as X-ray absorption near-edge spectroscopy, which can look at oxidation states, confirms 3+, 4+. But as you increase the charge, this red bar begins to increase, and that red bar is oxygen redox. So there is a mixture of manganese and oxygen redox within the material, and at the top of charge, on your right, it's dominated by oxygen redox. This behavior contrasts with layered oxides, where there's a strict transition between transition metal redox and oxygen redox. From experiment and simulation, we don't find any evidence of high valence manganese, 5+ or 7+. So the next question is, so let me summarize. The redox overlap here is there's a range of manganese and oxygen local environments in this disordered structure. And that's why there's some redox overlap between manganese and oxygen. So the next question is, what is the oxygen redox species? And there's a lot of debate about this. Is it localized holes on oxygen, for example, O-, shown on the top left? Is it dimerization of oxygen to form superoxide or peroxide species? Or is it full dimerization to form molecular O2 trapped in molecular 2? All three have been proposed, and there's evidence for all three. So we did some simulations first, some unbiased simulation. We had no pre-bias in which way the simulations would go. On the left is the pristine oxyfluoride, disordered rock salt. Lithium is in green, manganese in purple, oxygen's in red, and the fluoride's in grey. As we extract lithium on charging, we produce a large number of lithium vacancies, but also under-coordinated oxygen. And what we find from our modelling is evidence of molecular O2 being formed in these nanovoids, in these cation vacancy clusters. And that oxygen-oxygen dimer has a bond length of 1.2 angstroms, which ties up with experiment for molecular O2. Is there any experimental evidence for our simulated prediction? Yes, there is. So this is in collaboration with Peter Bruce and Rob House here in Oxford. They did some resonant inelastic X-ray scattering, RIX, at diamond light source, and they found that there is evidence for, I'm not an expert on RIX, but you can see spectra here on the pristine at the bottom, on the charged in the middle, and discharge at the top. For the charge state, there are some peaks and signatures for molecular O2. In fact, you can compare those signatures with lithium peroxide, and they do not tie up. They are signatures for molecular O2 rather than peroxide. So I'm showing you lithium peroxide at the top. So the next question for that dimerization, what is the atomic scale kinetics? And is there manganese migration? And the short answer is we're starting off with an MD simulation. So this is kinetic simulation. I'm showing you the lithium ions are shown in green, and you're seeing the manganese in blue, and the anions are shown in kind of orange and a light grey. What we're seeing straight away is that there is manganese migration, shown in a brown octahedra, but coupled to that is some oxygen-oxygen dimerization. And that's interesting, because these could be transient species, these superoxide and peroxide species, because the thermodynamic product is again molecular O2 trapped in these nanovoids. So what we're seeing is manganese migration, O2 formation, and some short-lived intermediates. And on discharge, the lithium insertion is into a different structure, and that leads to a lower voltage or hysteresis. And we published that a couple of years ago in Nature Comms. And this is elegant work by a postdoc in my group, Dr. Kit McColl. So what are the implications for that? Well, now we understand what's going on, we can suggest a design strategy to harness high energy density rock salts. We want to suppress O2 formation and manganese migration. And we've been doing that by modifying the lithium manganese ratio by composition tuning. And as I said, that was published a couple of years ago. We followed up that study to look at lithium-rich layered oxides, and we find some similar behavior that we find molecular O2 or nano-confined fluid molecular O2 within these nanovoids in this lithium-rich layered oxide. And that was published last year in Nature Materials. Because of time, I won't have time to go into details, but if you're interested, have a look at those two papers. So before I move on, I should mention important aspect to do with this series of lectures in terms of sustainability and the UN sustainability goals. And that's the 3 R's for batteries. We need to reduce, reuse, and recycle. We need to reduce, particularly the use of cobalt. We need to reuse or use abundant elements like iron and manganese. We need to develop economical recycling technology. And here I think beyond science, we need some politics and legislation here. So they're important for future use and recycling of sustainable batteries. So what's going beyond lithium? At this stage, I would usually ask the audience, have you heard of sodium-ion batteries? And some of you might put up your hands, some of you may not. If you haven't put up your hands, then you now have heard of sodium-ion batteries because I've mentioned it. And why sodium? Again, if I was an in-person lecture, I'd have got you to do some work, the audience. And I would have asked you to think about, in 30 seconds, the advantages and disadvantages of sodium versus lithium. Because I can't see you or ask you, I'll give you the answers now, but maybe you could ask the questions. So basically, sodium is more abundant than lithium, so it leads to lower cost. The disadvantage is that it's heavier and larger than lithium, and that leads to a lower energy density. So you won't see sodium in your phone in the immediate future, but you might see it in grid storage. So when the wind isn't blowing and the sun isn't shining, for those renewable energy technologies, we need grid level storage, and that's where sodium might come in. Sodium might come in for lower energy density EVs, electric vehicles like scooters or kind of small taxis in India and elsewhere. So you might hear, if you haven't heard about sodium-ion batteries before, you have now. Right, a brief TV break before I move on to dessert. And I was honoured, privileged and surprised to be asked to do the Royal Institution Christmas lectures for the BBC back in 2016. It's a real honour because Michael Faraday, who started them, is one of my scientific heroes. Here he is on the back of an old £20 note, delivering a Christmas lecture on the left in the famous Faraday Theatre at the Royal Institution in London. On the right is again one of my scientific heroes, David Attenborough, and he gave Christmas lectures many years ago, I think in the 1960s. Other heroes of mine, Richard Dawkins, have given these lectures, and Carl Sagan has given these Christmas. So I followed a great line of great Christmas lecturers. So I gave the 80th TV anniversary lectures. They were first broadcast on BBC in 1936, and I gave them in 2016. And this is the intro clip to my lectures, and hopefully you can hear the sound from your end. So they're called Supercharged Fueling the Future, and so the theme was energy. So for one of the lectures, I had to demonstrate how a battery works. And I said, when life gives you lemons, you make a lemon battery. In this case, from zinc or copper. You can use magnesium instead of zinc as well. And this is a great school experiment. But I didn't want to use one lemon. I told the Royal Institution and the BBC, I wanted to go large, very large. And we did. We built the largest lemon battery the world has ever seen using 1008 lemons that the group bought. We cut them in half to make 2016 lemon slices. So that was true cutting edge technology. In fact, the group said that connecting lemons wasn't the tough part. It was assembling the IKEA shelving was the tough part. Anyway, we got a Guinness World Record of 1,275 volts. Unfortunately, a group, I think it was in Denmark, broke our record 2 years later. So I'm not saying I felt sour or bitter about this, but I wanted that record back. And the Royal Society approached me before COP26 about doing something for schools. And I said, let's break the record. And we did. We use up to 3,000 lemons to generate 2,304 volts. So this is our new world record. And if you want to see a video of it, go into YouTube and type 3,000 lemons, and you'll see the video of our new world record. So I've currently got the world record, but don't tell others. Right, let me move on to dessert. For those Smiths fans out there, there is a light that never goes out. In this case, it's the sun. The types of solar cells out there vary. The most dominant is obviously silicon. Silicon dominates the panel, but there's been work on cadmium telluride, dye-sensitized, based on titanium oxide, organic and polymer solar cell. But the most studied solar cell material in the last 10 years have been halide perovskites. So first of all, what is a perovskite? So perovskite has this beautiful structure, this 3D structure. It's, in this case, lead iodide octahedra corner sharing to form a network, a 3D network. And at the A site, at that central site, is methyl ammonium. The mineral perovskite is calcium titanate, but in this case, it's an organic-inorganic halide perovskite. There are other acations like formamidinium and cesium, but this is the prototype material. So why is there interest in this material? This plot shows you why. Up on the y-axis is the solar cell efficiency, and along the x-axis is the year of discovery or the year of certification. As you can see in blue, this is silicon. Back in 1980s, it was about 15% for a single junction silicon. I should stress that this is just a single junction, not a multi-junction one. And you can see around now, it's about touching 25%. The perovskite was only discovered about 15 years ago, and it was languishing at only 3% back then. Within 15 years, only 15 years, it's now gone to about 26, 27%. That's unprecedented for a material to have that rise in efficiency. I forgot to define efficiency. Basically, it's light in, electricity out. And obviously, the higher the efficiency, the lower the energy cost, because you can use less material. However, there is a problem with these perovskites. They absorb well, they're easily made, they've got good charge transport. However, their long-term stability and their defect properties are a problem. So we wanted to get some atomic scale insights into why. So we started off at looking at their defects in ion transport. And it was elegant work of David Scanlon, Aaron Walsh and others, very early work, found that they are intrinsically defective with mainly vacancy disorder in the bulk. I'm showing you the equation at the bottom. V is for vacancy, not vendetta. V is indicating that there are vacancies in the structure, which I've highlighted in red. Red arrows, I mean. So this is a slice through the structure. So if there are vacancies, could they assist ion diffusion, which we don't want? These are semiconductors. We want just electronic transport. So we looked at ion migration in this material. But which ion moves? Is it the iodide that moves? Is it the lead that moves? Or is it the methyl ammonium that moves? And through our atomistic modeling, we found out very early on that's the iodide ion migration with a migration barrier of about 0.4 electron volts, 40 kilojoules per mole, which is fairly low. And that prediction was confirmed. Again, we had that value before experiment, was confirmed by impedance spectroscopy by Joachim Meyer and Michael Gretzel, and they found a very similar value. So the conclusion here is that these halide perovskites show mixed ionic electronic conduction, and that could be an instability issue. So this leads on to, can we passivate these defects for improving their stability using molecular passivation? So what is molecular passivation? So on the right, I'm showing you a schematic of a surface of a halide perovskite where there's an iodide vacancy at the top. Can we passivate that? And the reason why we need to passivate it is those vacancies mediate charge recombination, which we don't want. And that leads to poorer photovoltaic performance as a solar cell material. So molecular passivation can improve their stability. But what is the surface mechanism? What is the atomistic mechanism going on? So this is recent work with Henry Snaith's group and Nikita Noel here at Oxford, in Oxford Physics, and work with my group led by Vikram. And we published this last year in Science. We found some band gap universal passivation stable leads to stable perovskite cells with low photovoltage loss. So what do? We looked at mainly a former mammodinium-based lead iodide and used aminosilanes ranging in primary, secondary, tertiary. And what we found was that we could maintain the high efficiency for more than 1,500 hours. So quite decent long-term stability within these perovskite solar cells. And the one that worked best was this primary and secondary amine. And I'm not an organic chemist. In fact, I tried to move away from organic chemistry many years ago, but I've abbreviated to AEA-PTMS. So what's the surface passivation mechanism? It works, but why does it work? What's happening? And what we found is that it does indeed interact with the surface. What I'm showing you on the left is a slice through the surface. The purples are the iodide. The dark grey is the lead ions. And you can see the formamidinium molecules in the bulk. Above that surface, I'm showing you one particular aminosilane, in this case the AA-PTMS, the starting configuration. But what happens during the simulation? So let me show you what happens. We see a lot of dynamics at the surface. We see that molecule interact with that surface. It begins to align parallel to the surface, but bind strongly to the lead ions, which bridges the oxide vacancy. So there's strong binding. In fact, the strongest binding was for this molecule, which agrees very well with experiment, because we're showing that it's actually the highest binder. So let me show that as a schematic. On the left is the undercoordinated the pristine surface, showing the undercoordinated lead next to an iodide vacancy. And this is the final simulated surface, where the aminosilane now bridges that undercoordinated lead with lead-nitrogen bonds, but also bonds to another lead through the oxygen. So we're showing multidentate binding. So we're increasing the lead coordination, eliminating the effect of the defect, strong binding with multidentate passivation. So basically, this could be a passivation strategy using aminosilanes for durable, stable solar cells. And we're doing further work to understand and predict some other molecules as well. So what's next? Actually, what's being commercialized? What's being commercialized are tandem cells, basically combining, as the name implies, combining the best of two worlds, the best of perovskite and the best of silicon, to absorb a wider range of electromagnetic spectrum. So we can get efficiencies above 30%, approaching 35% now. And this has been commercialized by a company and other companies, but one company that I'm involved with, led by Henry Snaith, is Oxford PV. And they're manufacturing at scale these tandem devices. So let me begin to conclude, since I want to give some time for Q&A. So what's the future energy landscape? I think one thing is certain about the future. It's uncertain. We can say definitely on the political scale, there is a lot of, I would say, disruption and uncertainty. But by nature, I'm an optimist. And I think as a scientist and as a materials scientist, I think it's an exciting time to be involved with green energy, because we can contribute to so many different technologies in this green energy sphere. So whether it's batteries, solar, wind, wave, or even doing our bit in energy conservation, this is an exciting era. I'd like to acknowledge my research group, who do the bulk of the great work shown there, and the funders at the bottom left. I'm actually a good example of materials science. I had a knee operation this time last year, and that's an X-ray of my knee showing both metal and polymer within my body being slightly bionic. So that is showing material science in action in my body. So let me end with one slide with a quote. A few years back, there was a special exhibition to commemorate one of my another scientific heroes, Charles Darwin. I'm a devout Darwinist and humanist, despite my name. And there was a great quote, not from him, but by the French writer and philosopher Marcel Proust. And to me, it speaks to me about science in general and materials modeling in particular. And the quote goes like this: "The real voyage of discovery consists not only in seeking new landscapes, but in having new eyes." On that note, thank you for your attention. Thank you.
Thank you very much, Saiful, for a fantastic and really, really interesting talk. I know I have plenty of questions, but we've also got some from the chat. So we'll start with those. And we have one question. I'm not going to say who it's from because I will butcher people's names, but thank you in advance, everyone who submitted a question. And please do keep them coming. So you mentioned for the solar cells that show good stability over 1,500 hours, which is about 2 months. Can we assume that that will maintain similar stability over 1 year, 5 years, 10 years? Or will it degrade? Because presumably we want solar cells working for longer than 2 months.
No, that's a fair question. And obviously, it's always difficult in the lab to look at those kind of really long scales, like 5 years. In terms of accelerated lifetime testing, at the moment, sadly, they do degrade, but they don't degrade as fast as the normal controlled perovskite cells we're using. So there are some encouraging signs that there are strategies to try and increase the long-term stability. But that was a fair question. There is some degradation, which we are trying to minimize.
Fantastic, thank you. And then another question on the solar cells is for the tandem devices. Is there a specific ratio of each type of solar cell that brings the best efficiency?
That's another good question. I'm not a device physicist myself. I suppose the short answer is, I suppose, yes. there's going to be a different, in fact, they're not always double junction, they could be triple junction as well. And I imagine the ratio and the configuration makes a big difference. So I'd say yes to the answer, but in terms of details, I apologize not being a device physicist myself.
That's quite all right. I think it's the beauty of material science is that we need people with all sorts of different expertise.
Yeah, and
Nobody knows.
I'm happy to admit when I don't know the answer.
Next, considering the stability of the solar cells, is there any future for the application of perovskites in lithium storage?
Oh, that's a really good question. We did very early on. Oh, so the simple answer is probably no and unlikely. We did very early on look at, and this is a collaboration with a battery group and a PV, a photovoltaic group, and we were the modeling group in between. And we found that lithium intercalation or lithium insertion into these 3D perovskites, one was not very energetically favorable, but two, led to phase segregation. So they were not very good hosts for intercalation. However, there are 2D perovskites out there which might be more amenable, but my feeling is they still would not be as stable as the current oxides and polyanion materials that we're looking at the moment. So it would be curious to look at them. I would think it is unlikely.
Really interesting. And then another point, in comparison to the aminosilanes, does lead diiodide offer a similar effect of passivation, resulting in similar photocoulombic efficiency and operation times?
Yeah, so that question probably might have come from a perovskite PV person themselves. As though in the community, there is some different approaches. So people have tried to passivate using just the lead iodide itself to try and put an extra layer on top. So indeed, people have tried that strategy. There are downsides in terms of long-term stability, even with that passivation approach. But yeah, people are using even inorganic iodide approaches as well, and inorganic salts. Yeah.
Fantastic. A question then from Fran, and you've given some fantastic insights into the atomistic modeling of materials, and we're wondering if you could comment on the importance of modeling at different length scales and time scales, and the combination with experimental studies. You showed a really nice intersection with the experimental studies, both with the RIX experiments and the Japanese group.
That's a good question. So in terms of different F scale, exactly right. We'll try and link up increasingly on multi-scale approaches because obviously we're looking very much at the chemistry and physics level, but often these materials, you want to know more about them at the particle and the device level, and we can input parameters into those levels. And I alluded to how we're increasingly linking up on length and timescale, and that's using machine learning techniques. So rather than using a buzzword, in this case, it is actually a real application. We are using high quality DFT, quantum mechanical data, and using it to look at larger length scale simulations. In terms of linking up with experiment, yes, we always have to link up with experiment because the model is only as good as observation. So we link up with X-ray neutron diffraction on structure, spectroscopy on vibrational aspects, photoluminescence on PV, and electrochemistry on battery function. So yeah, a lot of my papers are combined modeling experimental publications.
Fantastic. Again, absolutely fascinating. And thank you for giving such thorough answers to everything. We are getting towards the end of our time. So I think we will wrap up. I think Juliana has a couple of slides just to share at the end. And in fact, it's quite timely because you mentioned the use of machine learning. That leads us quite nicely back to mentioning the top 10 emerging technologies, and encouraging people to submit their nominations. Juliana.
Well, if you could, let me just conclude by thanking all of you for attending. I know webinars are not always easy to attend, but thank you for joining us. I'd like to thank Ollie, Juliana, Chloe, and Fran again for the invitation. And for guys who want to know more information about my work, obviously I've just given a flavour. Just if you Google Saiful Oxford, my website will come up, and you can get all the publications from there. They're all listed in there. Okay,
yes, and we've also shared the link to Saiful's group webpage in the chat, so you should be able to there. And yes, thanks also very much to you, Saiful, for a fantastic talk. Juliana.
Awesome. Thank you so much, everyone. This is perfect. I had a lot of fun. I'm hungry now, Saiful, with all the food talk and electronic devices. Yeah, I'm gonna share my screen quickly just to close this amazing webinar. I hope you can see my screen. So yeah, as Ollie said, this combines really well with the top 10 emerging technologies of IUPAC. So nominations are open. Please feel free to make a nomination about the top 10 emerging technologies and also contribute to the Pure and Applied Chemistry Special Series. I'm also going to add another invite if you're interested to continue the conversation around green chemistry. We do have a platform for this. So Beyond Benign created with the ACS Green Chemistry Institute, a platform called Green Chemistry Teaching and Learning Community. So it's just a place where the community can talk about education and make sure the scientists, they know what they're doing in terms of sustainability and green chemistry when they go to the workforce. So it's free. Everything is open access and free. So please feel free to join us. Beyond Benign also has a connections series for those of you who are interested to keep talking about green chemistry and how we can move towards a more sustainable future. So this webinar series happens every third Wednesday of each month, and this QR code will take you to register for this. And also we have, if you know about K through 12 teacher, or if you are one K through 12 teacher that's in the audience, we do have a series for K through 12 education. So please feel free to join us. And with that, I'm going to send this to Ollie because he has some really cool updates about the IUPAC and IYCN work. So over to you, Ollie.
Yes, just a very quick last point. We mentioned IUPAC, CHEMRAWN and IYCN as some of the subcommittees of IUPAC. Some of the others are the ones you can see listed at the top: chemistry education, chemistry and human health, and organic and biomolecular chemistry. And collaboratively, there is soon going to be a competition for those undergraduates in the audience, making a short video about how chemistry can make a difference applied to human wellness, environment, and sustainability. It's an exciting competition, and there's quite a generous prize. So this will be launching very soon, and keep an eye out for those of you who are perhaps more of the TikTok generation than myself and good at making videos. That brings us to the end. I would like to take a moment to thank once again Saiful for his fantastic talk. Thank you all for your attendance. And of course, to Juliana, Chloe, and the Beyond Benign team for sorting out all the logistics and getting started at such an early hour.